Solve the following radical or rational exponent equations. Be sure to check for extraneous solutions. Extraneous solutions are the values that we get when solving equations that aren't really solutions to the equation. To solve a radical equation, we need to first isolate the radical. The radical is square root x plus 1, and it is not isolated because it is being multiplied by 2. So divide both sides by 2. Now that the radical is isolated, we can use the inverse operation of square root to remove this radical, which would be squaring. So square both sides of the equation. This leaves you with the radicand equal to 2 squared, which is 4. Solve for x. And now let's check. So x equals 3 is our answer. For number 2, make sure the radical is isolated. Now use the inverse operation of cube root, which is cubing. Now you have the radicand equal to 27. Solve for x. Now let's check. So x equals 18 is our solution. For number 3, isolate the radical. Oh, it's already isolated. So let's use the inverse operation of square rooting and square both sides. Because we're squaring a binomial, that requires us to expand. So we have x plus 1 quantity squared expanded equal to the radicand. This is a quadratic equation, so let's bring everything to one side and try factoring. We need the product to be negative 14 and the sum to be negative 5. That would be 7 and 2, with the 7 being negative and the 2 positive. Use zero product property to solve for x. This time we have 2 answers. Let's check to make sure that both are solutions. Remember, the square root of 1 is 1. The only time we have plus or minus is when we have an equation that said some variable squared is equal to 1. Then we needed to include positive or negative because we don't know if the x is positive 1 or negative 1. But in this step, we are evaluating square root 1. We are not solving by square root property of equality. Anytime you're evaluating roots with positive radicands and you're not solving an equation for an unknown value, your answer should be positive. The square root of 1 is not positive 1 or negative 1. It is only positive 1. This means that x equals 7 is our only answer. When we squared this x value in the beginning, we created a possible solution that wasn't a solution to the original equation. So you always have to plug your solutions in to make sure they make the original equation true. For number 4, we have 2 radicals. When you have 2 radicals, you want one of them on each side of the equation. So one on the left and one on the right. The inverse operation of square roots is squaring. So square both sides. Wow, that was super convenient. Go ahead and solve for x. Now let's check. So x equals 2 is our answer. Number 5 also has 2 radicals, and we already have one on the left and one on the right. This one is not quite as convenient though, because the radical on the left is not alone. And because we have 2 radicals we won't be able to isolate, we begin by squaring both sides. When you square this, you have a minus b quantity squared, which will expand to be a squared minus 2 times a times b plus b squared. And that's equal to the radicand. Let's simplify. Multiply the non-roots. We still have a radical equation, but this time we only have one radical. So go ahead and isolate this one radical and then square both sides again. Now you have the radicand of x plus 6 equals 9. So it looks like x equals 3. Go ahead and check. So x equals 3 is indeed our solution. Remember that rational exponents are just roots, or roots raised to an exponent. Be sure your radicand, or your quantity to the rational exponent, is isolated, and then use properties of exponents to turn x plus 30, quantity to the 1/2, into x plus 30, quantity to the 1. In order to do that, we will square both sides, because a power to a power means you multiply, and 1/2 times 2 is 1. Now I have a quadratic equation. Let's bring everything to one side and try factoring. We're looking for two numbers that multiply to give you negative 30 and add to give you negative 1. That would be 5 and 6, where 6 is negative and 5 is positive. Use the zero product property to solve for x. Let's check our solutions. Remember 25 to the 1/2 is simply square root 25. You can write it in root form or just continue to simplify. The square root of 25 is 5, not negative 5, making x equals negative 5 an extraneous solution, not a solution to this original equation at all. Making x equals 6 our only solution. For number 7, isolate the radical or the quantity to the rational exponent. Now we want to have 2x to the power of 1, not the power of 3 over 4. So what would multiply by 3 over 4 to get 1? Well, that would be 4 over 3. So we're going to raise both sides of this equation to the power of 4 over 3. 8 to the 4 over 3 is cube root 8 to the power of 4. The cube root of 8 is 2. 2x is equal to 16. Solve for x, and we get x equals 8. Let's check our solution. So x equals 8 is our solution. This time, let's solve a radical inequality. First, isolate the radical. Then square both sides. So x is less than or equal to 17. You could check by plugging in any number less than 17. I'm going to check by plugging in 0. Wait a minute, x can't be any value that's less than or equal to 17. There have to be two boundaries for this interval of solutions because we cannot square root a negative number. Our upper boundary is 17 inclusive, but what's the smallest number that's still a solution to this inequality? To find that other boundary, find the domain of the equation version of this radical inequality. Because h equals 1 and you have no reflection in the y-axis, the lower boundary of this interval of solutions should be 1. Or it might just be easier to think of what values can x not be. Well, the restrictions for x depend on the radicand. Whatever is under that square root must be positive or equal to 0. So it must be greater than or equal to 0. Solve this inequality to find your lower boundary for the solution set. Your solutions can be less than or equal to 17 or greater than or equal to 1. Actually, that's not an or statement. It has to be between 1 and 17 inclusive. In inequality notation, this is written as x is greater than or equal to 1 and less than or equal to 17. And in interval notation, we would write it as 1, 17, both inclusive. And there's your interval of solutions.